In this video, I'd like to introduce you to atools. It's a tool to simplify running parallel tasks on HPC systems. So what kind of tasks are we talking about? Well, basically the tasks are non-interactive and you want to execute many independent but similar tasks. That could be potentially inefficient due to load imbalance and hence resource usage, and there's the potential of failures of tasks. Some use cases. So for instance, parameter exploration. You have quite a number of parameter sets which you can and want to compute independently of one another. Or another case is process many files, also independently. So you can do this, of course, with job arrays, which is a feature supported by most workload managers, including Slurm. But you'd have to do the bookkeeping. For parameter exploration, the only thing you get from a job array is a number. How do you get the specific set for the parameters you want to compute in the task with that ID? It's up to you. Also, with respect to bookkeeping, which tasks succeeded, which tasks fail? Yes, you can figure that out, but it's inconvenient to do so. And then, of course, data aggregation. Suppose that each task generates some data, and you want to aggregate all the data into a single file. Then how do you do that? Again, it's not rocket science, but it's up to you. So that's essentially where atools comes in. So let's take an example, and suppose we have this very nice application that predicts the weather given three parameters: the temperature, the pressure, and the humidity. It's a somewhat sophisticated application in the sense that it can run on multiple nodes. It's implemented using MPI. So basically in my resource request, I specify that I'm using 2 nodes and 36 tasks per node. So for a total of 72 MPI processes running on 2 nodes. And of course there is the rest of the resource specifications such as time, memory, and so on. So basically I could submit such a job for each triple of temperature, pressure, humidity I'm interested in. And visually, that would be a table with 3 columns. Column for the temperature, 1 for the pressure, 1 for the humidity, and each row in that table would represent a single computation. So essentially, I could submit many batch jobs, as many as there are rows in my table, and each time I'd have to edit it, ensuring that the correct values for all these quantities go into that job script. And that have many of those. Okay, so essentially what I'm doing is I have many, in this case, multi-node computations. Of course, this is a somewhat sophisticated example in the sense that we have a distributed application which we're running, but this equally well holds for multi-threaded applications or even serial single-core applications. Okay, so we have the setting. Now, what's the solution to make this easier? Essentially, we can use AEnv, which is part of atools. So rather than thinking about a table, we actually create one as a comma-separated value file, which has 3 columns: temperature, pressure, and humidity. And it contains the names of those columns. Okay. So in my job script, I do a few modifications. I load the atools module. And of course, you could load a specific version, but if you don't specify that, then typically you will get the latest version, which is most likely what you would like. That, of course, by itself doesn't do much. It's the next line, the source statement, that actually does the magic. What it's going to do is, using the data file that you specified, and based on the array ID, it's going to select the line in that data file which contains the values of the quantities that you want to use. So basically what it's going to do is it's going to initialize environment variables that have the same names as the columns in your data file, in your CSV file, and give them those values. So of course that means that the column names should correspond to valid variable names in Bash. So of course no spaces and preferably no weird characters. Okay, next step is on the command line to load the atools module again, because we need another tool which is called arrange, and then we have to get the array IDs, and that's where arrange comes in. It takes as an argument, command line argument, the data file, so again our CSV file, and it will output an array ID range, which we can use with sbatch, which we use as usual, except for the array command line option with the array IDs we just computed. And that will submit your job, and you can sit back and relax while things happen. So, in a data exploration scenario, what would be the steps? So the first step is to write your Slurm script with parameters, so with these environment variables, and don't forget to load the module and add a line to initialize those parameters using env. Then you create, for instance, an Excel spreadsheet with data and you convert that to CSV. Or, if you prefer, you can directly either generate your CSV file from some script or write it directly, depending on what you're doing. And then you submit with sbatch, and of course don't forget the array option, where the range of array IDs is determined using a range. So where does the bookkeeping come in? Well, that's using logging. And logging is used for, on the one hand, recording which tasks succeeded and failed, and that allows us to redo failures, and it also allows us to do performance analysis. So, of course, the scheduler itself provides logs, but those are not always convenient and even not always user accessible, depending on the configuration of your cluster. So basically that's where atools comes in and tries to facilitate things a bit so that things can be more efficient and easier for the user. So how does it work? Again, it uses a small tool called alog, which is of course part of atools. So before you start the actual work in this particular task, so in this case the MPI run for weather, you use alog -- state is start. So this will insert an entry in the log file that indicates that this particular task has started. And then when that task is finished, you have alog with state end, and also the exit status of this particular task. So in this case, the $? is in fact the exit status of the last command that was executed. So for this example, it's the result of MPI run, the exit status of MPI run. If MPI run ran successfully, $? is going to be 0. If it ended in failure, then $? is going to be positive non-zero. And this gives rise to a log file, which looks like this. So in its extension, you will have the job ID of this particular array job. So it's easy to match a log file to a run, to a job. And it will contain entries for each task, 1, 2, 3, etc. In this example, it says where it was started, on which compute node, and when it was started. You also have ending events, which can either be completed or failed. And if it failed, it also specifies the exit status. In this case, the exit status was 1 for task 2 that failed. This can be used for many purposes. One of them is monitoring. And again, a range helps us here. So you can monitor either running or finished jobs. You call arrange on the command line with the data file you're currently processing in that job, the log file, which of course must exist, so your job should be running, and you specify the summary option. And that will give you the number of tasks that have been executed successfully or failed. Now, suppose that not all tasks finished successfully, in the sense that some of them were actually terminated by the scheduler because the wall time was exceeded. So in that case, what you want to do is you want to run the array IDs for which you have a start event but not an end event, or for which you don't have a start event in the first place. Again, arrange will give you those array IDs based on, of course, the data file, but also the log file of that specific job. And then you can use that range of array IDs again by simply submitting your batch job as before, perhaps increasing the wall time to accommodate the jobs that couldn't finish in the wall time specified by default. If jobs actually failed for some reason, then you can also require them to be redone. And that's with the dash redo option of arrange. Then it will include also those job IDs or those task IDs for which the processing failed. Of course, this will only make sense when you know the cause of the failure and, of course, can mitigate for it. For instance, suppose that some tasks didn't finish successfully because they didn't have sufficient memory, then you can redo those tasks, but in the subsequent sbatch command, you specify more memory for these tasks. Another thing that atools is going to help you with is aggregating data, and that's using areduce. So for simple cases, it's quite automatic. Your files follow a particular pattern, the file names. So in this case, each array item has produced output dash the job array id.txt, and you want to aggregate those into output.txt. So you simply specify the range of job array IDs with dash t, and those will be substituted into the file pattern that you specified. So this takes care of incomplete data, failed work items, and in that case you can use arrange again, in this case with the dash list completed option, which ensures that the only array IDs that you get are indeed those of items that completed successfully. It also takes care of the correct order of the work items, and for CSV files, you can use the dash mode CSV option, and that will ensure that there only is a single column title row at the top of the file, rather than what you would get if you would naively use cat, which would almost produce the same result, but with multiple column lines. For non-trivial aggregations, you can again use areduce, but now you need to specify an empty file, and you need to specify a reductor script or executable. So basically, what's the semantics here? Essentially, the reductor can be any executable, and it appends the new data to an existing file. So it takes two command line arguments at minimum, the name of the file in which you're aggregating the data, so that contains all the output data up to that point, and then the name of the file, which contains the data to append to this aggregated file. So that executable can take extra command line arguments, and that's through the dash reduce args command line option, which then will be passed to that reductor executable. Sometimes we require some job statistics. So load balance is mostly taken care of by the scheduler, but questions which you may want to answer is, did all tasks take approximately the same amount of computation, or are there some tasks which take longer than others? So that is something that a load can help you with. So basically, you can analyze runs from multiple perspectives. For instance, you can report on the work items or individual tasks using the dash dash list tasks option. Or if you're interested mostly in load balance, you can report on the nodes by using the dash dash list slaves options. And then you just call a load with the log file of the job you want to analyze. So with respect to CSV formats, atools is pretty flexible. So it tries to determine the CSV dialect by reading part of the file and analyzing it. The default it reads is just 1024 bytes, which is plenty for most CSV files. However, in special cases, for instance, if you have a CSV file with many columns, you might want to specify a larger number of bytes. So you can do that explicitly by using the dash dash sniff option and the number of bytes you actually want to use to determine that dialect. For CSV files with a single column, which are actually not CSV, just use dash dash no sniffer and everything will proceed as you would expect. For more information on atools, you can check the documentation, and of course, each command has its own help with the -h or -h help option.